Hey folks, so we are back at section 2.7, the second part. So if you will go down in your notes, right underneath reflections, we're gonna work some examples here. And we're gonna deal with translating a graph vertically. So if you were to use your calculator to graph x squared plus 2, you will notice that the parent parabola, here's the parent parabola here in purple, it's going to shift up 2 units. It's going to shift up 2 units. And what you find out is that anytime you add or subtract outside the parent, you're going to shift vertically up or down. So notice that I'm adding here outside of the x squared. So we're going to shift our graph up 4 plus 2, and if it were x squared minus 2, we would shift our parent down. So to put it in one of our nice gray boxes here, given a function g, and g here is going to be, I like to call it the kid, where we have our original parent, because f is the parent, our original parent plus something, so we are adding outside of the parent. And by the way, that c could be negative, so it could be adding or subtracting. So what will happen here is the graph of g is going to be exactly the same as f, but it's going to be translated up or down that value of c units. Up or down. The graph, the kid graph, is then called a vertical translation. Vertical meaning up and down of the graph. Horizontal translations, notice again, G here is our kid, where F is our parent. Notice now that my adding and subtracting is going to be on the inside of the function. It's going to be inside of the parent. Here my kid is outside the parent. Here my kid, notice, is inside of my f of x function. And what happens here is the kid graph is going to be exactly the same, but it's going to be either translated right or left, and it's going to be backwards from what you expect it to be. I'll show you that here in just a moment. This is called a horizontal translation of our graph. So here's an example where I have this plus 4, I have this plus 4, and it's inside of my squaring parent. If you were to graph this on your calculator, you would notice that the kid actually shifts to the left, where plus 4, we might think it would go to the right, but it actually goes to the left. So that's why I said it's going to be backwards from what is expected. So we have here, this is again our parent in purple, and we're shifting to the left 4 units. So when we add or subtract inside the parent, this is going to be a horizontal shift. So this is going to be backwards from what we think. Now, this particular table is just simply a conglomeration of things that we've already done. So we've got, if it's outside the parent, this is and positive, we're going to go up. If it's outside the parent and minus, we're going to go down. If it's inside the parent and plus, we're going to go to the left. That's backwards from what we expect. And if it's inside the parent and we're using a subtraction there, it's going to go to the right. Again, backwards from what we expect it to be. All right, so let's make this make sense. And we're going to do these without the aid of the graphing calculator. So let's look at all of the things that we've already learned. We know that the subtraction sign, or the negative out in front, not subtraction, negative out in front, is going to cause us to reflect over the x-axis. We now know that anything on the inside of the parent is going to make us move either right or left, backwards from what we expect, and anything on the outside of the parent is going to make us move up and down vertically. So we can say that we're going to move to the right one, we're going to reflect over the x-axis, we're going to move up 4. We know that this is the quadratic or the parabola parent. So I already have some coordinates marked there. Notice that what was 0, 0 went to the right one. It went up 4, and because we have a reflection, instead of it being concave up, now it's going to be concave down. And so we can go ahead and draw. All right, moving over here to this one. Notice that the negative in the front is going to cause a reflection. The inside is going to cause us to move to the left 3, and this 2 on the outside is going to be a vertical stretch. All right, we know that the parent is the absolute value parent. Remember, that's the V graph. All right, so then the reflection, that's going to cause us to go upside down V. That vertical stretch by 2 is going to cause us to be skinnier. We'll talk through how much skinnier, and then we're going to shift to the left 3. So let's do the shift first. You notice I went to the left 3, and this is going to be that corner point, that top point there. Now, in the normal parent, we would have gone right 1, down 1, right 1, down 1, right 1, down 1, right 1, down 1, and we would have done the same thing on the other side as well. But this kid does everything twice as much as his parent does. So we're still going to go right 1, but instead of down 1, we're going to go 2. And so right 1, down 2, right 1, down 2. And the same thing on the other side. So left 1, down 2, left 1, down 2, etc. So we can go ahead then and connect the dots. All right, and then we have this graph. Remember that this is a reminder of what the square root graph looks like. And we are going to have a vertical shrink by 1/2. That's the guy out front. We're going to go to the left 2, that's inside. And we're going to go down 3 because it's on the outside of the parent. So let's talk just about the left 2 and down 3. That part is kind of easy. So we've got left 2, down 3. You can see that I've already got this piece of my graph. And so we've got our left 2, down 3. Now, normally this guy would have gone to the right 1 and up 1, and that's without a vertical shrink. All right, so normally he would have gone right 1 and up 1. This kid, though, is only going to go right 1 and up 1/2 because he does everything half as much as his parent does. And then when we did back in section 2.6, when we introduced the library of functions, when we introduced this parent, we also said that he's going to go to the right 4 because the square root of 4 is 2. He would have gone up 2, but instead he's going to go half that much. So he's still going to go to the right 4, but only up 1 because half of 2 is 1. So it's a very short square root graph. All right, to sum it all up, any changes on the outside of the parent function is going to cause vertical changes. Anything on the inside of the parent function is going to cause horizontal changes. Now, I'm not going to fill out this chart for you because all of it is already filled out somewhere above in the same set of notes. It's just sort of a one-stop shop here where you can get everything all in one place. Now let's take a look here at a couple more examples. You notice that I've got this function graphed. This guy is a weird one. He's not one of our normal parents, but it is a parent. You've got a graph of a function defined by y equals f of x is shown. Use this to sketch each of the following. So basically what I have here is I have 4 kids that I want to graph. All right, whereas this is the parent. So let's get a description for each one of these. First of all, this guy is the parent minus 2. So that means we're going to shift down 2. This guy, because my minus 2 is on the inside of the parent, that means we're going to go backwards from what we expect. So he's going to go to the right 2. Kid number 3, or kid C, notice he has 2 things. So on the inside, this guy is going to tell me to go left 1, and on the outside is going to go up 2. And last but not least, this guy is going to be a reflection, but it's going to reflect over the y-axis because it's on the inside of the parent. All right, so then let's see what each of those looks like. So when you take this guy and you have to shift him down 2 units, I kind of just go by the major points. So you've got 1, 2, let me do that with the laser. 1, 2, 3, 4, 5 major points. If you shift all 5 of those points down 2 units, you can just connect the dots. And I've already done that for you here. There's my 5 major points, and I can just connect the dots. All right. If I want to go to the right 2, again, I take all 5 of these and I'm just going to shift to the right 2 units. And so that's what you see here. All 5 of these are shifted to the right. I'm going to try to show both of them there. All right. For the third one, we want to shift everything 2 directions. We want to go to the left 1, but we also want to go up 2. So all 5 of those points, left 1 and up 2. And last but not least, we want to reflect everything over the y axis, the y axis. All right, so back up at the parent, that means this guy is going to go over here to the -3 because that's shifting. The y-axis is my mirror, so this guy is going to go over here. This one's going to stay put. This one's going to go this direction, and this guy is going to go all the way over here to -4. All right, so we've got a backwards version of what we had earlier. All right. Now, looking at symmetry and testing for symmetry, we have 3 different types of symmetry. You can have x-axis symmetry, where my x-axis is the mirror, y-axis symmetry, for my y-axis is the mirror, and then origin symmetry. I don't actually have a mirror, but here's the way that you would want to think of this. If you can turn your graph upside down and have the exact same graph, then you've got origin symmetry. All right, so we're going to be looking at graphs to know what our symmetry is. Is it x-axis, y-axis, or origin? Because of our parents, we already know what to graph. So this guy is going to be my absolute value graph, shifted down 3 units. And we would say then that our y-axis is our symmetry, our mirror. So we have symmetry with respect to the y-axis. This guy needs to be rearranged a little bit. So y equals mx plus b. So this is just a line. And so here's a graph with a y-intercept of -6 and a slope of 2/1. And you'll notice that my x-axis, it's not the same on top and bottom. So it's no x-axis, no y-axis. And I cannot turn it upside down and get the exact same thing. So also no origin symmetry. This guy, remember the parent? Parent looks, actually, I think I have this on the graph. It's in green dash. That's my parent. And then we are going to reflect it over the x-axis, and we are also going to make it skinnier. So we're going to have a vertical stretch by 2. All right, and this is one that if you can turn your paper upside down, I can't do it on the iPad because you won't be able to see it on the screen, but if you can turn it around upside down on your paper, it's the exact same graph. So this is an origin symmetry. And last but not least here, we've got, this one has a reflection. The x is a reflection. The 2 is a vertical stretch. This is our normal quadratic. So it's upside down parent, a bit skinnier than normal. And so we would say this one has y-axis symmetry. All right, and that's it. That's all that we have for this section.